Alright, it's just part two, looking at B part two, how to outline it. Alright, let's see if this thing gets it. Let's see if it's showing. Alright, great. It is showing. Alright, so the thermal conductivity of the brick. So you're given the thermal conductivity of the brick, thermal conductivity of the foam, and we're supposed to calculate the thickness of the brick, which would have the same effect, the same insulating effect as 5 centimeter of foam. Alright, so it's the process. Alright, so for it to have the same effect, the rate of heat transfer must be the same, right? So we can say, since it's basically power, the insulating power of the brick needs to be equal to that of the foam. Alright, so we know that this is the equation or the formula for conduction is this. Theta 2 minus theta 1 over L. Alright, so for them to have the same effect, these need to be the same. So in terms of how you would show the markers that you understand the process, you could equate both. So you'd have, let me just use B for brick. Alright, so that should be equal to of the foam. Two minus theta 1. Alright, so let's look at the question. Alright, so we can imagine, instead of having the foam here, we have another layer of brick in between. Alright, so we can consider what would be the same, what's going to be the same if we replace the foam with the brick. So in this equation that we just, what's going to be the same? So we can simplify this expression.
The temperature change doesn't, or the difference in temperature doesn't change.
So same difference in temperature. So same insulating effect. So
I
we
believe,
can we can
is it
remove
same length as well?
same length, same thickness. No, remember we
Oh
just
no, no,
said
it can't be same thing. Yes, no, no, that's what we're looking for.
yeah,
Same area.
same area. Alright, so that was the issue I was having yesterday. So the remember that A is the cross sectional area. So it would have the same, it's not the thickness, but the cross sectional area. So remember the view that we're seeing doesn't show the cross sectional area. Alright, so we can remove the area from this. Alright, so it essentially is going to end up being thermal conductivity of brick over thickness of the brick is equal to the thermal conductivity of the foam over thickness of the foam. Alright, so
Oh, oh, this is what I was doing yesterday. And then you just transpose it to get the thickness of the foam.
yeah, alright. So I just wanted to make the process clear as to how we got it. So what were the values again? So thermal conductivity and thickness. So for the foam, what's the value for the foam? Well, let me just write it as it tell me. It was 0.16.
No,
Yeah,
zero
zero
point
point
zero 0.016.
0.16. Yeah.
And the thickness was of the foam was point
No, I think that's what we're trying to find, isn't it?
no man of the
No,
foam
no, finding
of
the
the foam.
thickness
Oh
of
no, the brick.
um zero point zero
Five.
0.05
Yeah,
meters.
0.05 meters.
Alright. And then the thermal conductivity of the brick is known.
Yeah, 0.48.
Now we're trying to find the thickness of the brick. Alright, so it's just a matter of transposing them. So the thickness 0.16. So depending on how you transpose, should get the same answer. Um,
So it ends up being the same 1.5.
yeah, so 1.5 meters.
Yes.
Yeah, 1.5 meters.
Right. Yes. All right. let's say this is like about
41.
4,000.
Or
Not drawn to scale. So let's say 35. All right.
Wait, what are we doing now?
No, we're just first of all just reviewing, make sure we're okay. All right. So if just going over the concept of resolving, if we're resolving that vector, so let's say there's a force here, just checking to see that we're all good. This. All right. So how could we resolve this force into
In the horizontal or the vertical component?
so we're doing both. So let's start with
If y is not equal. Uh, 35.
so just we don't have any values to resolve. So just how you would say how what would you have to do to if we are given a value for f.
Alright, so for the y direction, I have 35 sine f. Just easy.
35
um,
35
I
sine f.
disagree.
What you have then
It's F sine 35.
f sine 35.
So,
Oh, yes,
so,
actually.
so why do you
Yes,
make
sir.
that y?
Oh, yeah. My bad, my bad.
So they always make the horizontal y and the vertical x. But like the axis on a graph.
The vertical y and the horizontal x. That's what you said?
Other way around. The vertical wait, no, that's easy. Why does it look weird? It looks strange for some reason.
What do you mean? What do you mean?
Probably because it's on this side. It's still
Oh.
Oh,
it's still the same y.
Yeah, no, okay. Yeah, no, no, it looks like it makes more sense. It
alright.
looks more familiar now.
Let's do it
Yeah,
on this
so
side
f.
because it's a triangle, you know, so it's the same this
On
side.
both sides. But
Yes.
but it's so rarely on that side just looks strange.
Yeah. I did it this
F
way to show it that
half.
it's a triangle, so it's just trig ratios again. So if you're trying to find fy that is opposite to the angle, so that would be if we're finding fy that's sorry, that's sine sine theta equal opposite, that's fy over hypotenuse, which is f. So this is where it comes from. So fy would just be f sine 35 in this case. Alright. And x, which triggeration would apply to f and fx then?
Cosine.
So cosine that's adjacent over hypotenuse. So fx is going to be equal to,
F cos 35.
great. So all of this is necessary just in, especially for it appears in a lot of
Projectile
subjects,
motion.
projectile, circular motion, um, yeah, mainly
Vectors.
those,
Vectors
yeah,
just there.
yeah, they, they, they don't usually give vectors by itself, especially with how the exams are set up since I think 2019, where it's just 3 questions. So you're likely to have a lot of mix up happening. So uh, let us we can yeah, all right. We can start with the circular motion. Because this circular motion has, you'll find it has some concepts that overlap with module 2. So harmonic motion, that wave type stuff. So let's start with circular motion. So I actually looked at some equation from circular motion yesterday. All right, let me see what are the equations on this thing. It's 52. Oops. All right, so we have some equations here. All right, let's see what you remember. So in terms of circular motion, you can be asked about the conditions. What are the conditions required for circular motion? Let's see if we remember that.
There should be a force moving towards the center of the circle.
So there should be a force towards the center. What else?
So the object's velocity must be tangential to its movement at every point.
Right. So I just lost it. Just lost it. All right. So the centripetal force, we know it acts towards the center, and it's, as I said, it's tangential to the linear velocity that keeps it moving in a circle. So what would you say about the speed? So during circular motion, what can we say about the speed, the linear speed that is?
Is it constant?
Yeah. So the linear speed is constant, but the velocity is changing. We know the velocity is changing because
The direction is changing and velocity
The
Direction
is
direction
change.
is changing in a circular motion.
yeah, so direction is constantly changing, so it is experiencing an acceleration. So it is accelerating. All right. So we have these equations. All right, and there are different types of scenarios with circular motion. So I'm sure you've seen. So you have it there, the vertical circle. What happens when you have a vertical versus a horizontal circle? You have questions like with a car going around a bend or a plane aircraft. So all of these you can apply circular motion principles. So, oh, by the way, this W looking symbol, what is this again?
That's omega.
An angular
Angular speed.
velocity.
Angular velocity.
Angular velocity.
Yeah.
So yeah, both it can be denoted by both. What is omega? Because there's an important. How would you calculate omega?
Omega equals 2 pi over t as well as 2 pi s.
So 2 pi over t or 2 pi f. So it's a very important equation because again it will appear in waves again. So this same omega. All right. All right. So I want to go to one of the recent years, but it's not under the document. All right. Give me a sec, trying to bring up this paper. This is 2021. This is 2023. Alright. Hope it's not my net. It's acting up. Alright. Can start from the very top. Alright, so there are some graphs there. Alright. So we can look at the simple harmonic motion question. So there are a couple questions on this we can look at. So this is 2023. Alright, so somebody can start us off with this one. So differentiate between precision and accuracy.
Accuracy refers to how close your recorded answer or your recorded value was to an accepted value, and precision is how far apart your values are, how close together your values are, your recorded values are.
Alright, so accuracy, that's the closeness to the quote unquote true
Accepted value.
value.
Yeah.
And
Precision is how close your different recordings were, or your different values are to each other.
Alright, great. Alright, so we have a table here with some measurements which were made to determine the density of the material whose true value was determined to be that. So, of course, we can comment on the accuracy and we can comment on the precision of these measurements.
So they are highly inaccurate, but they are very precise. They're highly inaccurate because they're very far away from the true value of 3.75, but they're very precise because they're all 0.01 away from each other.
Alright, so it's not it's not close to the true value, so it's not accurate. Doesn't represent an accurate measurement, but the values themselves are close to each other, so the measurements were precise. Alright, no problem with that.
Uncertainty?
Yep, uncertainty.
Um,
Fractional error. So right.
so the uncertainty of f over f is equal to the uncertainty of m over n plus, did I say plus or minus here because it's an expression? Or did I say plus?
Plus
It's plus.
plus the
Plus,
uncertainty of r.
plus the uncertainty
Changing
of
r.
u squared over u
It's
plus the uncertainty of
that's
r.
u.
Wouldn't,
Wait, no, it's
isn't that
not
V?
u.
Oh, sorry, the v. My bad. Yeah.
Sir, what symbol is that, I may ask?
Yes,
As
sir. What
about
symbol
us.
is that?
Delta.
Because I usually see delta. I'm used to
Is
delta.
that delta?
That is not delta.
That is not
That's
delta.
not
So I'm to my
delta.
triangles.
Exactly. Isn't delta a triangle?
That's the capital. What it is it's capital delta. You know these things are.
Sir, that's a thing?
Yeah,
What?
it's a
Wait,
why I have the
Could they
equal.
Greek letters? Are they
Okay,
Greek
that
letters?
makes sense. That makes sense. That would make sense.
yeah.
Alright, so
I remember
Plus
They're
delta
changing r over r,
delta
and
R
then you're
over
gonna
R,
have
and then 2 delta V over
two,
V.
two
Yeah.
delta v over v. You need the brackets.
No, you
no, you
don't.
don't.
It would be just plus 2 delta V over V.
Alright, so that's all I wanted today.
well, one mark to be fair.
But yeah, that's all they wanted.
Okay, alright, just the expression. Alright, so we have this experiment. An experiment is performed using the apparatus in figure 1. A small disk of mass m on a frictionless table is attached to one end of a string. A string passes.
Sir, the questions aren't showing.
Oh, sorry. So, yeah, so a small disk of mass m on a frictionless table is attached to one end of a string. The string passes through a hole in the table. That. Alright, so you have this setup. So radius r, time period t. Alright, so the first question, get rid of that thing, is state two conditions that must be satisfied is if a body is moving with uniform circular motion. So
Yes, sir, didn't we already say this already?
yeah, so what did we say?
We said there must be a force acting towards the center. That will be the centripetal force, and that the linear speed move is tangential to the motion of the object.
Also, the acceleration must always be perpendicular to the velocity, and there must be a constant speed.
Yeah, so we must have a body traveling at constant speed um, at a tangent to the circular path. You must have acceleration towards the center of the circle, or force towards the center of the circle, um, perpendicular to that velocity. So 2 where am I? Where am I? Where am I? All right. So here's how they can ask a derivation question now. Show that the relationship between the period t, the radius r, and the masses m and m is given by the equation t equal 2 pi mr square root of mr over mg. So still under circular motion. So should still be thinking about circular motion equations. All right. All right, let's go to the whiteboard. So 2 pi. All right, so we have some. So we already have an equation for
Oh wait, sir. So for the equation that you use for this be mrw squared, mr omega squared.
so because
Yeah.
if you look at what's in the equation, you have
Yeah.
square root m r over mg. All right, so yes, this mv squared over r is an equation for centripetal force. We also have m. All right, I remember.
And then wait, sir. So since you, so based on the end result that you're supposed to get, I'm assuming you'd have to make F be equal to mass times gravity and then change omega squared into 2 pi over t.
Yeah, so t is in omega. So that's why I said these equations for omega, can't forget them. Remember that omega is 2 pi over t or 2 pi f. Alright, so if we want time period, an equation for time period, we have to use the one that has time period in it. So m omega squared r is equal to mg.
Sir, that's a capital M, right?
Yeah,
Okay.
so we can substitute for omega. If we substitute for omega, it's going to be 2 pi over t squared r. Um,
And then you just transpose for t.
transpose. Alright, so you're going to have, then get rid of everything else. So 2 pi um, people transpose different ways. So whichever way you're comfortable transposing, it's up to you. To just reciprocate the equations to make life simpler. I mean, for me. So we could have t over 2 pi. Right? 2 pi. So that's your 4 marks. Alright, so it starts with equating the centripetal force with mg. Alright, any problems with that? Okay, good. So we just
Good, sir.
good. Alright. Next question is a graph, but let's see what we can do with information, or we can at least say what we would do with the information. Plot the graph now. Let's see. All right, so look at part 3. So it's a red equation, that same equation in the form y equal mx plus c to show that the gradient is that. So look look at what exactly is being plotted here. So what are you plotting here? What are you supposed to plot? Or is supposed
We're
to
supposed to plot t square against m over 1.
1 over
1 over m.
1 over m.
So
My bad.
t squared versus, right? So t squared versus 1 over m. So yeah, it shows you what they did to that equation. So what would you have to do to the equation, the original equation, based on what's
Square both sides.
so square both sides. So can square both sides and see what happens. So if you square both sides, you're going to end up with t squared is equal to what?
t squared should equal to um mr 4 pi squared over mg.
So get rid of the,
That's it.
yeah, just get rid of the square root and for mg. So this is why um you are plotting t t squared versus 1 over m. So if we isolate 1 over m,
It should be t square equal 4 pi square mr over g, then 1 over m by itself.
so mr over g. So y equal to mx plus c 0. Alright, so we could plot the graph to see what would happen with that. Let's see. Hmm. Okay, you'd have to do the graph to do this. Alright. So 2, 1. As we would need to do the graph to do this, but let's see if I can find.
You just transpose for G. Well, no, you wouldn't. You would equate the gradient from the equation, the 4 pi square mr over G, to whatever the gradient was of the graph, and then transpose for G.
Yeah, so let's say our gradient was, let's say 0.05. So let me estimate something to have something working with.
So what was M and R? They're given, I'm almost certain.
Zero, 5. What was M and R?
Little m and R. Little m and little m 0.013. Little r was
0.8.
So my gravity, it is not Earth. We have 8.21.
That would give it 8.21. If so, what would G be equal to?
G is 8.21.
No one in terms of the equation, the when you transpose.
G is equal to 4 pi squared, 4 pi square mr over the gradient number, which was 0.05. I just switch.
So, alright, so all you're doing is substituting. Alright, no problem, no problem, no problem.
Wait, how did you get 0.05?
You would have to do the graph. It was an
We did
estimate.
not.
It's an
We,
estimate.
we, we picked something.
So you would have to do the graph and get the gradient from your
Oh,
equation.
okay. Alright.
Wait, is Sir speaking or not?
So next question.
Um,
Next question.
oh,
Newton's law of universal gravitation. It states that, if I remember correctly, it states that the force of attraction between two objects is directly proportional to the product of their mass, whilst inversely proportional to the square of the distance between their centers, or something like that.
Right. So what's the what's the equation that governs that one though?
It's capital G times M1 times M2 over R squared.
That's equal to what? You start with capital G.
Wait.
Isn't it force? Yeah.
The force of attraction, yeah.
Yeah.
Alright, so that's gravitation. Alright. Alright, it said with the aid of a sketch, explain why the equation EP, so potential energy equal mgh, in which G is that cannot be used to calculate the potential energy of an orbiting Earth satellite.
So the sketch that is about a difference in the distance, as the distance is the same from the center of the Earth to the Earth's surface, the center of the Earth to however far the orbit of the satellite is.
Mhm.
So the sketch a circle and then a dot in the center of the circle to show the distance from the center of the Earth to the surface, and then a circle around it to show the distance from the center of the Earth to the orbit of the satellite. So the value for G is inaccurate because the distance increased for the satellite.
So like you look at satellite up this up or something like that.
Yes, that's the satellite. Then you can draw a circle for that. Well, I didn't draw it like this, or wouldn't draw it like this. I don't think I'll draw the satellite itself.
Okay.
I'd more likely draw the orbit of the satellite.
The orbit of the satellite. The orbit. So
Uh,
what's the issue? What you say is the issue with why is it we can't use the 9.8 again?
So the distance between the center of the Earth and the Earth's surface, which was the first line, yeah, that line, would have the gravitational pull be 9.8. But because the distance from the center of the Earth to the satellite is larger, that would mean that the force acting upon the satellite would be smaller because the distance is inversely proportional to the force of attraction.
Yes. So the farther away you get, the weaker the gravitational force gets.
Yes.
And it's a inverse square relationship. Alright, so objects close to the Earth, of course, we can say it's 9.8.
Yes.
Research. Alright, where's that? Alright, so just so in your explanation, um, just to say that the gravitational strength, the field strength, is inversely proportional to the square of the distance. So the distance that the satellite is a very far distance, is large, much larger than the radius of the Earth. So the value for G would be much less than the 9.8. Right? So I think that's enough. Along with the diagram, that's enough to get it. I think it was 3 marks. Where is it? Right here. Alright, so the 9.8, that 9.81, that's only for objects that are close to Earth. So once it's far from Earth, then we can no longer use that relationship. Alright. In the next one. Alright, simple harmonic. So we can jump straight to the simple harmonic.
State the two conditions that must be satisfied for the oscillatory motion of an object to be considered simple harmonic.
Wait, is it asking for a specific tool? Because from what I know, there's like multiple of them.
The acceleration
You're just asking
is
for any?
proportional to the displacement.
There must.
I don't know about many. When I say many.
Yeah, there's mainly two.
There's mainly.
The acceleration is proportional to the displacement, and acceleration must always be in the opposite direction to the displacement.
Opposite direction.
I'm not sure about the second.
I mean, it can reduce it's in always acts in the opposite direction.
Or you could say towards the equilibrium position if you don't want to say. Yeah, if you don't want to say opposite direction.
Yeah, usually I say towards a fixed point.
All right, so
the acceleration must always be going towards a fixed point, and the displacement should wait. No, what was the wording?
Proportional. The acceleration is proportional
Yes,
to the displacement.
and the acceleration should be proportional to the displacement from the fixed point.
all right. So before we look at the other questions, just to look at the equations that fall under this topic. Let's see the ones that are on this doc. Um, hmm. Mm, mm. All right, with these equations, especially the ones with the trig ratios, you have to kind of be a little careful in terms of whether you're using sine or cos. So if you use sine, always remember, I think the best way to remember it, just put sine 0 or cos 0 in the calculator. Because what's sine of 0?
0.
Zero.
Sine of 0
And then for cos, it's 1.
is 1. So 1 is at 0, and we can take the other one to be maximum. So if it's starting, if if you have a scenario where it's starting from 0, then you know that case you have to use
It's assigned.
the sign, right? You're starting,
And then cosine is when it starts at maximum.
it starts at maximum. All right, so you have to look at those. All right, so we see the omega appearing again. So if it's displacement, it's A. A is what's A in this case?
Amplitude.
Amplitude.
Amplitude should represent the maximum displacement. So, and then omega, which we know is 2 pi. So,
Over T.
Over T or
2
times
pi
F.
f.
Or 2 pi F. Yeah.
Yeah. All right. So we can write those. So it's going to be, those are going to be more useful. So amplitude. Uh, that will look like that f. All right. So you have similar equations for the velocity. So we can, it looks similar. Oh, by the way, so let's use the case of a simple pendulum. So if you have or it's the same situation as a swing. So if you're on a swing, it's going to oscillate back and forth about the equilibrium. So you have displacement, you have velocity, and you have acceleration. All right, so let's use letters. So A, this is E for equilibrium, and B. All right, where is the velocity at its max? Where would you say at what point is the velocity at maximum? So where is it?
At E.
So velocity is max at E. So let's look at the max and midpoints. All right, at So that at x, where is it? At, sorry, the distance, displacement is max at what point or points?
B and A.
So A and B. Alright, where acceleration is max where?
It has to be the same as displacement because they're proportional. So A and B.
So it has to be A and B. So great. Alright, so at A and B for the velocity, what's the velocity at point A and point B then? What
Same
happens to the velocity?
0.
Zero. Alright. Yeah, because it has to stop in order to go back in the other direction. So when it reaches that point, you have what? A restoring force. Alright, so displacement is of course zero at the equilibrium point. So it's zero at A or B. It's going to be zero at E. It's going to be zero. Alright, so just wanted to check that. Alright, so similarly for velocity v, we can have a similar equation where can be cos or sine depending on the situation. So same form. Alright, but v max, so one of the equations for v max is they don't have to tell you what v max is. V max
You amigo.
yeah. Alright, so so you also have this equation as well, v squared. So which is where this relationship comes from. So omega squared a squared minus x squared. Alright, let's see if we will need any of these equations in these questions. I think we'll answer some of these already. So the displacement of y of a body undergoing simple harmonic motion is given by that. So alright. Okay.
A is amplitude and W is
Not W.
Angular velocity. Or
Angular
omega is
angular
angular.
velocity, omega.
W. The W looking thing.
Right. All right. So there's a graph. So on the okay, it's a sketch though, so it's not. So on the graph provided, on the grid provided, sketch three graphs to show how displacement y, velocity v, and acceleration a vary with time for an object undergoing. Alright, so it's related to what we were talking about. So use the same time for all three sketches. So how would the sketches look? So basically just discussed it a while ago.
So the ones between um displacement and acceleration should be the same because they're proportional to each other.
Is it the same though?
Is it
it the
not?
same? Is it the same? Same. So remember what we said about the conditions for simple harm. What were the conditions again? So this was I think the
Acceleration
condition.
towards a fixed point,
uh,
and the acceleration must be proportional to displacement from the fixed point.
Yeah, yeah, but remember that the acceleration
Oh no, it's
is
slightly different
yeah.
because at the start displacement is at a maximum, isn't it? But acceleration starts at zero.
No
I
man,
think.
they are proportional, but the point is that they act in different directions. That's what I wanted to get at. As I was trying to get at.
Hmm.
Alright, so they need to be acting at different directions. So depending on where you start your graph at, so let me kind of do it. I mean, you're doing three different graphs, but if you start at zero for displacement, for example, uh, line, no move line, then so yes, when displacement is at its max, acceleration is at its max as well. But so well, this would be the acceleration versus time. Would be the distance versus time. All right, how would the velocity? I think that was the third one. The velocity sketch look. Let me draw a third line. So how would you sketch
Uh,
this one?
it also starts at zero, and then it goes.
This one would also
Oh,
start at zero. These
does
two
it? No.
started at zero.
The velocity will start at the maximum.
Yeah. So the distance and acceleration they are proportional, But if you look at this over here, when displacement and acceleration are at zero, so at the equilibrium point, that's when velocity is at its max. So that's why we have grids, so we can line them up properly. All right. All right. Any problem with those? With that?
No, sir.
No, sir. Good.
All right. A light helical spring of spring constant 30 Newton per meter hangs vertically from a fixed support and carries a mass. So assuming that Hooke's law is obeyed, calculate the extension produced in the spring.
So we'd use
Sir,
S
so,
equals
oh,
to KE to solve this
yeah.
equation.
And then
But
I'm
you'd have
gonna
to also
assume.
use
Oh yeah, continue.
F would also have to equal to mg.
Yeah.
So by that would say E is equal to mg over k, and then we just substitute the values to find the answer.
And wait, Carl, the reason why it would be mg is because it hangs vertically, right? So it would be the tension.
Yeah, tension, so gravity and the
Yeah.
mass. That's
So
what
it's mass times gravity. Okay, cool.
All right, so let me write that down. So you say Hooke's law
Equal ke.
but you said to equate this
And
to
then F would be mass times gravity since it's hanging vertically.
Is gravity 10 or 9.81 for this system?
9.8.
9.81.
Yeah. Wait, does it matter if we use 9.8 instead of 9.81? Like, will they penalize us? Because I always use 9.8.
I don't think it matters.
well, I would
Okay.
use what you give. That's fine.
Yeah, but most of the times it doesn't give. Most of the times it doesn't give
Yeah, it doesn't give
gravity
it.
because they just expect us to know it. So will it
That's
matter
true.
if
No,
we
man, they
use?
give it, man. I promise you, they give it.
They do. I have not seen that.
You've never seen that before.
I've seen it on CSEC, but I have not seen it on a Cape paper.
Yeah, I think they just expect you to know it.
So then there you just plug in the values and solve for the extension.
And I promise you it's there. So if you scroll up to the top, just use it. If you're unsure, just scroll up to the top of the paper. 9.81.
Oh, so you should just use 9.81 then
Yeah.
to be safe. Alright.
Where was it? Where was it? What are we trying to find again? Sorry, I lost the question. I'm trying to find the extension. Okay.
Yes. So let's round it to 0.1.
You got 0.1?
Well, 0.098. So I said let's round it to 0.1.
Let's try and not round it.
Let's use standard form. Let's say 9.81 times 10 to the minus 2. Is that correct?
10 to the minus 2. Yeah, if you. Yeah. Alright, or 0.0981. That's fine. Calculate the maximum kinetic energy of the mass if it's displaced a further 0.45 meters. What was that graph for? Okay. So max kinetic energy
Sir, I have a question.
mm-hmm.
I did a calculation, but I want to know, since it said a further 0.045 meter, do we add the extension to it from the previous question?
Yes.
We do. All right. So I have the maximum kinetic energy has equal to half kx squared. And in this case, x would be the 0.098 plus the 0.045.
Uh,
Wait, Carl, what did you get for the answer?
Let me just put it in the calculator and tell it. That's didn't wait.
I got 0.3067.
yeah. All right. So you can. This actually has you have different ways you could calculate it, but I think that's the simplest way to do it. You could actually use half mv squared, but you would have to find what v max is, which is um, amplitude times omega. So if you're willing to go that route, fine. But that is much simpler.
So what's the answer?
0.3 as another guess, 0.307.
Yes,
Uh,
0.307.
yeah.
All right, this looks like another graph question. Mm. All right. So diffraction grating and everything there. All right, you can do that too. So remember the questions, as you can see, are now much larger, 30 marks. So they can mix different concepts in one question.
Wait, sir, how many questions are there on a physics paper?
Three.
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 Just three questions? Dear
But
God.
they
There
have
are,
A, B, C,
Ah,
and
yes,
D.
part A, 1, 2, 3, and 4, part B.
Yeah, you have A1, A2, then B2,
Yeah,
B3.
boy.
So that's specific.
yeah, I don't know why they did that. So it used to be six, but um, the questions were more separated. So now they can join different concepts in one question. Um, all right, so diffraction. We talk about diffraction. That's how we're referring to.
So the fraction of light is, if I remember correct, it's the bending of wavefronts as they travel across a boundary like through a gap.
All right. So are the spreading, I would use the spread because we don't want it to sound too much like
Yeah,
diffraction.
yes, pretty. Yeah.
So spreading of light as it passes through a gap or slit. All right. Now to the calculation. So as it relates to diffraction grating, diffraction grating, let me go to the equations for that one. Oh, somebody can
Wait,
yeah.
I was going to ask for this question, would you use the d sine theta equal m lambda equation?
Yeah.
Okay.
Alright, did I pass it? Alright, so I was asking somebody to share back the link in the chat because I think probably one or two persons joined afterwards to the folder with some other resources. So if you still have it. Alright, so I would have shared this one yesterday where you can look at each um, topic for the equations. Alright, somebody shared it. again?
Yes, sir.
Okay, great. Right, I don't see no. Alright, so for the diffraction grating equations, you'd have to look in the actual topic. I thought it was at the front. Alright, and I think you should have the derivations there as well, yeah. So this is one of the derivations you can be asked. So it would be good to know this. Alright, so what do we know here? What is it that we're trying to find?
N.
We're trying to find N, capital N.
Alright, so what would you do first?
To find N, you'd need to find D first. So I suggest you find D.
Alright, so find D first. So using that equation, we can find D.
Yes, sir. D sine theta equal N lambda.
Alright, so let's do that. This one. Alright, so we need to know what N is, what lambda is. We'll have theta.
Sir, N is the order, and lambda is the wavelength.
Alright, and we know all of that. So we can calculate. So N is 1, right? N is 1.
Yes, sir.
And wavelength 5.89 times 10 to the minus 7. And we'll have theta. Alright, so somebody do a quick calculation of D then.
I got D to be 1.28 times 10 to the negative 6. But I suggest someone check that because I'm not sure fully.
Could you repeat it, what you said?
I got 1.28 times 10 to the negative 6.
I have 2.46 times 10 to the negative 6. Ooh.
What?
I got
What was
1.2.
the equation? What was the equation you used, Carl?
I multiplied n by the wavelength and divided by sine theta.
And divided it by what? Sine 27.7?
Yeah.
Wait, what did you have? What
Wait,
did you
no.
put for N?
I think it's 1. Yeah.
Wait, yeah, then how did you get. Yo.
Question, did you divide theta by 2?
No.
Sir,
I got
question.
I got 1. 1.27 times 10 to the negative
Yeah.
6.
It says
1.27. It says what?
maybe I'm thinking about it too hard. The angle between the two first order fringes on either side of the normal is 27.7.
Oh, Carl, that just means that on both sides it's 27.7, not that like it's split between the two sides.
Oh, okay. All right.
Angle between the, the two first order fringes.
Because it says on either side, so it's 27.7 on both sides.
All right, you're correct. You're correct.
Yeah, so D is 1.28 times 10 to the negative 6. And then you'd use that to find N because N is equal to 1 over D.
You know. Yeah, I think Carl is right though.
Wait, I am. Wait, I am.
Yeah. The angle
Oh
between
my days.
the two first order fringes. That sounds like from one fringe to the other, and not necessarily from 0 to 1. What do you think?
No, but sir, it says on either side. So wouldn't that suggest that
So
it's 27.7 on
in
both
between
sides?
them, yeah.
So
It's
that's what I was
27
thinking.
in a fringe, then 27 again, then another fringe.
Yeah, that's what I was thinking.
I don't think so. Doubt it.
Yeah, they worded it very oddly. So very odd. But I divided theta by half.
All right. Find n. So n, the relationship between d and n is what's the relationship?
They're inverse, so D equal 1 over N and N equal 1 over D.
Wait, but what was our D? Is our D the answer where the angle is divided by 2 or the one where we just take the angle?
I'm leaning towards it having to half it, the one where you half it. So that's the one I'm leaning
Okay.
towards. So between
So the angle
uh
13.85.
Yeah. So I got D as 2.46 times 10 to the minus 6.
So just reciprocate it.
The unit is whoa
Um,
meter per ruling or something.
for N
Yeah.
it's rulings per meter, per millimeter.
No, I'm talking about D.
Oh, D. D is just millimeters.
So N is the inverse.
I would. All right, but since they, I don't know, since they wanted it in millimeters though, because if you look at what they asked for, I'd probably just convert it first to millimeters, and then you do find n. How about that? Because you
So
might get
multiply by, well, yeah, multiply by 1,000. So it becomes to the negative 3.
so 2.46 times 10 to the minus 3 millimeters.
Yep. And then we find the inverse of this, which is, I'm sorry, to negative 1, 406.42. 406.42.
All right, so 406.4. So 406. That's fine.
So that's it for this question.
That was the last question. I don't think so. This one, that's the last question. The highest order of
Order.
fringes obtained. So calculate the highest order of fringes obtained on each side of the normal.
Each in big capital letters.
Yeah, it's on each side. So in terms of degree, what's the highest possible degree when it comes on to this that it can obtain? So you have to think of it from that aspect. So the highest order must be at the highest possible degree. So what's the highest possible degree that we can get from the diffraction grating? Highest value for theta.
Is it the 27.7 or the 13.85?
No, that's for the first fringiness. That's the very first one. So you have others like 2 and so that the higher the order, the angle is going to increase. So think about it from a geometric or mathematical standpoint. It's the highest angle you can get for these fringes?
360.
360.
No, not it. 360 would mean it's going back towards
Oh
the
yeah, it would
center.
be going back. Yeah.
So no, not 360.
180.
So it'll be 180.
180. 180. 180. 180. Wow. No, not still not 180. Where is it? Let me see if I can find a screen for you. So look at this thing. Remember, I know you say on either side of. So look at, yeah, the one in the middle.
Oh, it would be
The
90.
90.
It's 90.
90. So the highest possible
Yeah, it's 90.
would be 90 degrees. Alright, so
So,
we're using the same
so,
equation to find what the highest
and
possible value of n is.
so we're basically saying that when the angle is 90, what is n? What would be the highest possible order of fringes?
Mm-hmm. So, so n
Wait, what's the value of d again that we're using?
D is 2.46
4.6.
times 10 to the negative.
2.46
Yeah.
Yeah. Times 10 to the negative
to the
3
negative.
if you're using millimeters and 6 if you're using meters.
No, I use the meters because remember the wavelength. The wavelength is, you can mix units. So Wavelength is
Wait, for the it's to the negative of -3 for meters?
-6.
Negative
For meter,
6.
okay. Um, so I got 4.17, which would just be 4 for the order.
So the highest would be 4.
Yeah, according to these calculations.
All right. Anybody's got 4? Agree?
Putting it into the calculator now. Wavelength was 5% to -7. Yeah, I got 4 as well.
Great.
I second 4.
4. All right. I wanted to touch one of the cycle diagrams. So before we do any more of these type of questions, let me look back at that.
Question.
Yeah.
What was the calculation we just did?
What we're calculating this as in the question or
Yeah, the question.
so you're supposed to calculate the highest order of ranges obtained on each side of the normal.
Okay.
I would say that
Um,
the highest order would be based on the degree, the highest possible degree
what was the formula used?
same d sine theta equal to n lambda. So trying to find n.
And we're finding n.
Yes. So the highest order would
Alright. Did we
represent
use d as in meters or millimeters?
in meters, as the wavelength is in meters.
Okay. What was the answer?
4. What 4?
4th order.
Okay. So you did 2.43 times 10 to the negative 6, and then you divided it by 5.89 times 10 to the negative 7?
Yep, yeah.
Okay.
And then you'd get 4 and a decimal, but since orders can't be in decimals, you just use 4.
All right. Thank you. Thank you.
All right. So we're going to look quickly at this thing would only load. Module 3. Going back to one of the module 3 questions. But as I said, they like Hooke's law in terms of module 3. They like asking about Hooke's law related stuff. And the mechanical properties seems like they prefer that, asking that for some reason. But I think this is it. 2, 3. This is it. This is so blurry. Why is it so blurry? Alright, the thing about module 3, we have to remember it actually starts with the temperature stuff. So it's similar to what was done in CSEC, where I had to become familiar with the different types of thermometers and like the scale, temperature scale, and all of that. So it's a little more in depth in CAPE. So that's a graph though. Let's move down to this part. So particular part D. So starting with D. So we never got to go through a question like this where we have, so the first law of thermodynamics, yeah, we kind of looked at it, but a full question based on it. All right, so we have another thermometer is used to measure the temperature of a monoatomic ideal gas in an engine as it goes through its cycle. The quantity of gas in the engine is 0.0052 moles. There are 4 stages in the cycle as shown in table 3. Alright, and you have stage A, they give you the values, so they tell you what's happening. So at stage A, the gas has a pressure of that and a volume of that. That stage. So try to see if you can sketch. So based on what's being said here, see if we can sketch what the diagram would look like just based on the table and what's written below. So read it a little bit.
Wait, sir, what are we supposed to do?
So sketch the diagram to represent all of these stages, the 4 stages. Just to It doesn't show it. Oh, they don't have a diagram looking like that. Okay. Mm. Alright, so let me see if I can find an image. There's not one in the book. Alright, so remember there are some different conditions. You have isobaric, so that would refer to pressure. You have isovolumetric, you have isothermal, and you have adiabatic. So see if I can find an image that has all of those, so you can see how the stages look. So thermal dynamics. Let me try this one.
I don't know what was rubbing your arm. Look at him, man. Look at him, man. Mr. Sir, speed up now. Or Mrs. Man, speed up now, man. Mrs. Mom? What if she's not married? I don't care.
Somebody's
Mom,
unmuted.
Mrs. Mom, Sash.
Christoph.
Yo, Christoph.
Alright, let's go. Yes, I was looking for an image to kind of, so if you have PV plot, this is how you expect. So if it's constant pressure, P is on the y-axis. So if it's constant pressure, we expect the line to be
Straight
horizontal, right?
and straight, yeah, horizontally straight.
Yeah, if it's constant volume, then it's going to be like that. So vertical. You have isothermal and adiabatic. They kind of look similar, it's just one is just steeper. So you just need to draw that curved line to show the change. In isothermal though, one thing to note, isothermal, just because there's no temperature on the graph, there's no temperature axis, right? But it's just to note that if it's isothermal, that means that there's no change in the internal energy, right? So if we're asked about that, if the temperature is not changing, then there's no change in internal energy. So that's the result of having an isothermal process. Alright, so delta U would be 0. So if they say isothermal expansion, it would be delta U is equal to Q plus W, uh, plus or minus W, depending on if work is being done on or work being done by the gas. So if in isothermal, temperature is the same, is constant, that means that delta U 0. So the implication from that would be Q is equal to that. So that's how, so you can look at how the internal energy equation, that first law of thermodynamic equation, is affected by um, the various conditions. If it's constant pressure, that means P is constant but V is changing. Then we have delta U is equal to Q plus W. And work, how do we calculate work?
Work is equal to pressure times change in volume.
Yeah, so P delta V. Alright, so that's for constant pressure. For constant volume, what's the implication for constant volume then?
Don't you mean that
There's no change.
There's no change in what? And there's no what?
There's no work being done.
Yes, if the volume is not changing, then delta V is 0. So what's going to happen to the equation then?
W equals 0.
W equals 0, so that means
That delta U is just equal to Q.
Q.
I know Q is NCV delta T. That's how you calculate that, since it's constant volume. So
Wait, sir, you said U is what is equal to what? Oh, Q. Oh, I see. Wait, what is CV?
water heat capacity. Water heat. Alright. So remember we have other equations like PV, nRT, and NKT. So have to look at what you are given here. Alright. Alright, so going back to the question in stage A, so we can talk about how each stage will look. So you have the pressure and volume that it starts at, and they say constant volume heating. So that line, how would you expect the line for stage A to look? So
Wouldn't it just be a straight line going up?
a straight line going up. Right. So the pressure will increase. So if the volume, if you're heating at constant volume, pressure is going to increase. So we can have a situation where stage A have something like that. That's supposed to be straight. Stage A. Alright. So pressure, volume. The initial was 6.0 times 10 to the something. To the 5 or something like that. Times 10 to the 5 pascals. And volume was 5 times 10 to the minus 5. And 5. So almost as if they cancel times 10 to the minus 5. Let's put it there. Times 10 to the 5. Alright, stage B. Adiabatic expansion. So how, based on what you saw from that one, if it's adiabatic expansion, that the next line is supposed to look how?
Steeper.
So steeper, and is it a straight line?
Well, it's not. It's a curved line that shows the relationship between pressure and volume is inverse, but it's steeper than isothermal.
Alright. And it's an expansion. So if it's expansion, that means that what's happening?
The volume is increasing.
Yeah, so volume increase is increasing, and then so it increases. So let's call that, let's say B. Oh, even we spoke about isothermal, but in adiabatic, the heat is zero, so there's no heat transfer happening. All right, so that's the difference between isothermal and adiabatic. In stage C, there's constant volume cooling. So constant volume, how would that line look? So if it's cooling, what's happening?
If it's cooling, that means
Well, the temperature is going to fall, but what else is going to change apart from the temperature?
pressure.
Would it be the pressure?
So if you
The pressure is going to fall with it
It's going to decrease.
because of pressure. Now.
all right, so according to stage C, it's, what does it say about that? It's, so 8.6 would be where the adiabatic expansion thing stopped. And then stage D just says back to A. Alright, so how would you get back to A? Because I know that let's see what this said. Yeah, we just draw a line back to A. So back to A.
It's closed. We have a shape.
Alright, so it will look something like that. Alright.
So what allows us to just draw the line from C back to D? What is the rationale behind?
Why? Because it says so in the table. So
So, so
uh,
it's just a straight line. Okay, sir.
yeah. So da. Because if you look at stage C, we know stage C was a constant volume cooling from 8.6. So we know that that is where stage B would have stopped. Stage B would have stopped expanding when the pressure is 8.6 times 10 to the 5. Alright, so that's where stage C starts. But how do we know where to stop? You know, where to stop at? Or where the pressure stops at? We know where stage C stops at because of where D starts. If we look at where does D start?
With pressure at 6 times 10 to the fifth.
Yeah, so that means that's where C stopped. And 6, if you look at stage A and stage D, the pressure they're the same.
It's the same. Yeah.
Yeah. So we know that if we're going back to stage A, it will just be a horizontal line going back there. Alright? So it's not a guess, they're all connected.
What almost be?
Stage B,
Yeah, there's idea right.
so the adiabatic expansion. So we don't know where it we don't know where stage A in terms of the pressure, we don't know how high, what's the maximum pressure it went to. Right? We don't know. So that's why on my sketch, the 8.6 that I have here is not at the top. 8.6 would be where the adiabatic expansion. Let me see if I have that correct. Because they didn't list any starting pressure or starting volume for adiabatic. So they kind of expected you to understand that if it's an adiabatic expansion, it's going to look like that. It's going to have that curve going down. Alright, so in the table for B, they didn't tell you where it starts or where it stops, but it's connected to A. So whatever pressure A did reach, that's just where you're going to start from. They didn't tell you where, so you wouldn't put that on a sketch. But we know where it stopped because we know where C starts from. So they're all connected. So we know that the adiabatic stopped at 8.6 because C starts at 8.6. Times 10 to the 5. Alright, so let's see what the actual questions for this are. And it's a sketch. Not really a sketch because, I mean, yeah, it has to be a sketch because not all the values are filled in. So you can actually use the grid in the different stages, use a ruler. It'll end up with something looking like what I drew for 4 marks. Alright, so first calculate the initial temperature of the gas, stage A. So the initial temperature at stage A. So what equation can we can we use? That all the information. What's the initial temperature? At all.
Do we use PV equal nRT?
So PV equal nRT. Do we have all of those values?
Yeah, because we have pressure,
Yeah.
volume, we have the moles, we have gas constant, so we just need to find T.
Which is what we're looking for.
Yeah.
Alright, so PV is equal to nRT. So N is what, 0.0
50052.
R is a gas constant. That's at 8.31.
Wait, sir, quick question. Wait. Oh, wait, never mind.
So you have the initial pressure and the volume. So we can solve for T. So PV over RT. So
Wait, sir, which question is this? Which number question is this?
this is, you mean on the paper itself?
Yeah, on the paper. On the
I
paper,
think
what
it's
number is it?
question 3.
3, okay.
Yeah.
So you mean PV over NR? Because we're looking for T.
Yeah. Over the cell, we'll go PV over RT.
Yeah.
Okay.
So we go to the top so I can see the numbers for the volume, man. It's 5 times 10 to the 5th. No, that's -5. And N was 0.0052 times 8.31.
NR.
Wait, sir, what's the gas constant again? It's 8.31. Is it times 10 to the anything? Is it times 10 to the anything or just?
Just
Oh,
8.31.
okay.
Yeah, no, this answer. Oh no, I see why it looks weird. This is the -5th. Okay, I have 694.25 Kelvin.
So 694. Point what?
Yes, sir. Same, I got the
25.
same thing. 0.25.
Alright, so 694 Kelvin. Alright. Let's see what I can do with that. Determine the heat heat energy supplied to the gas going from stage A to stage B? Heat energy supplied to the gas going from stage A to stage B. All right, so what is heat energy? Let's see.
Heat energy
Is
is equal to N, and then is it the molar molar it was a constant for the specific object and the change in temperature, I think.
let me see. Oh, no, they actually don't give you. Oh, my bad. Oops. All right. So you have to know this one. Actually, have to know this one.
Which one, sir?
That is so blurry. Yeah, what were you saying for heat now? Which equation?
I was thinking that it was going to be the one, but I don't think they gave it to us where you use the molar
Or the molar heat capacity.
yes, the molar heat capacity, that's what it's called. But I don't think we got that. I don't think we were given the information.
Yeah, but you know the molar heat capacity.
You do? So go back up. Quick.
NCCR, CB.
We have 10. That's 0.025. Oh, sorry, 0.0052.
Mhm.
And we have the change in 10? Oh, yes, we do. Because it is from what the number they gave us, which is somewhere up there. So can you go up to the table? Yes, they did. So it's 800 subtract the 694.25. That will be multiplying with, where is it? The molar. Sorry, I'm not seeing it. Sir, where is it? So where's the molar heat capacity?
Molar, I think, pretty sure I mentioned this yesterday. All right, so I thought they would have given it on the paper, but apparently it's something that you need to know. So the molar heat cap, sorry, the yeah molar heat capacity. Why was that so hard to say? Is for CV is 3/2. I use 3/2 R. So
So it's 3 over
it's
2
a constant.
times 8.31.
Yeah.
I feel like this is something that they should give you though.
But they give you R, so they don't have to give you 3/2 R. And if
So you just have to remember that it's 3/2.
yeah, and if it's CP, it's
Okay.
just 3/2. Well, 3/2 R plus R, which is really 5/2 R. That's 5/2. That's it, yeah?
Yeah, it is. So the Q that I have calculated, or the heat that I have calculated, is times 6.85.
You got 6.85. What was the delta T? What was the delta T?
I have 800 subtracted by 694.25.
Alright. I think CV will work out to 12 point something. So, 12.
CV works out to. I may have put the wrong thing. I may have put 2/3 instead of 3/2.
CV is 12.47.
Okay. Alright. Yeah, so it's
Yeah,
just
12 point.
so,
Yeah, 12.47. Rounded.
and when you put all of that, you got what?
I'll put it again because I may have not written it down.
Wait, where did the 800 come from?
The 800 that was in the table.
Times
Oh, okay. Oh,
And we just,
I get it.
yeah, the other 10 times 8 points. Yeah, it's the same. 6.85.
6.85.
Yes.
Yes, sir. 6.85. Well, I got 0.86, but
I didn't round the 3/2R. I just put 3/2 and then multiplied it by the 8.31. So this is probably the exact one.
Alright, cool. Alright, so that's the heat energy supplied to the gas. Yes. CV delta T. Alright. Where am I? Okay. Alright, define internal energy of a gas. What's the internal energy of a gas?
could you just say that it's the sum of the supplied energy plus the work done?
Sum of sum of the well, that's the law though. So that's a law of thermodynamics. So in terms of internal energy, remember internal energy is really just assessing the total energy possessed by the gas. So total potential plus kinetic energy. That's internal energy. Alright, so
Also, potential and kinetic. Okay.
yeah. If the gas is ideal, there's no potential as well. And then So we would state the law of thermodynamics here. We could talk about Q, change in internal energy, Q plus W, and state what each term is. Alright, so with reference to the first law of thermodynamics, calculate the change in internal energy of the gas in the engine as it goes from stage B to stage C. So change in internal energy with reference to the first law of thermodynamics. So stage B. So I had said something about the adiabatic, or did I say about the adiabatic thing again? What do you remember about it? What's the significance of that? That stage B is the adiabatic. So
Means temperature is not constant.
temperature
Was
is not
that it?
constant. Well, I mean that's true, but there's a specific condition for adiabatic. So when it's constant temperature, there's no change in internal energy. So if it's isothermal, no change in internal energy. But if it's adiabatic, something is zero. What is zero in adiabatic expansion?
Oh, Q is 0.
There's no heat transfer. So I think if you apply that to the first law of thermodynamics, what's the what's the implication of that during an adiabatic expansion? What's the implication?
It would mean that the internal energy would be just equal to the work.
So when they say determine, where is it? Determine the reference to the first law of thermodynamics, calculate the change in internal energy of the gas as it goes from stage B to stage C. So it's just to state the law of one mark is to state the law of thermodynamics, which is that, and to say that so delta U is equal to Q plus W, but that Q is equal to 0. So it would just be equal to the work. And they gave you the value for work. Right. So hence why this question is only 2 marks. They gave you a value for work on for that, which is 37. So where is it? Alright, so the change in internal energy here is just 37 joules. Alright, next one. The gas in the engine completes the cycle by going from stage D back to stage A. Oh, that's a three part. And so state what happens to the volume, temperature, and pressure in this process. So
The pressure stays the same,
which
I
was
think.
going from back from D to A.
Yeah, pressure stays the same.
It was a lie. So pressure, I believe pressure was constant. Volume was decreasing.
So volume decrease, pressure stay the same.
And the temp, what happened to the temp? The temp
Wouldn't
was
the temperature also decrease?
decrease. So in this process, are we going from A to D to A? Are we doing work on the gas, or is the gas doing work? So that's why you need to
get
consider.
the gas is doing. Wait, no, I'm actually not sure.
So can be, so that this is our direction. All right. So if the gas is doing work, that means it's going to cause the thing to expand. All right. So if the gas is doing work, we're going to have expansion. If we are compressing the gas, we're doing work on the gas.
So we're doing work on the gas
Yeah,
because
yeah,
it's getting smaller.
yeah. And the if the pressure is constant and we are decreasing the volume, the temperature is going to go up, right? Temperature is going to go up. So consider it from that aspect. We're putting energy into the gas. So we can think of it like that, energy into the gas. So internal energy will increase, temperature will increase.
Yes, sir.
All right. Let me see what was on. So the next year after 2019 would have been 2021. It's a post-pandemic. Um,
Wait, sir. I have a question regarding the last one that we did.
last
For
question.
yeah, the last question we just did. In the answer, we said that pressure would stay constant and volume is decreasing.
Would decrease, yeah.
So why can't we use Charles' law and say that temperature is also decreasing? Because what was it? When pressure is constant, that would mean that volume and absolute temperature have a directly proportional relationship, proportional relationship.
Okay. So you said Charles. Remember that all of these, the Charles law, Boyle's law, they're all related to the kinetic theory. So it is what this is how we got the ideal gas equation. So using Charles law, Boyle's law, the combined gas equation is how we got the ideal gas equations. All right. So principles remain true. I don't know why it's taking forever.
Wait, but said that it said the opposite though. I'm 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 unsure on why we said temperature would increase.
What does Charles law state?
That for a fixed mass of a gas
Yes.
at constant
Constant
pressure,
pressure.
yes,
Mhm.
there is a directly proportional relationship between the gas's volume and its temperature, and its absolute temperature.
See, so
So pressure was constant
constant.
and volume was decreasing. So shouldn't temperature be decreasing as well?
Alright. So what approach did they want you to take?
Did they want you to go using um, thermodynamics? Well, no, but this is technical thermodynamics as well.
Yeah. So with reference to thermodynamics, um,
Sir, but that's what G though. I mean for H.
mhm.
In H it didn't give any restriction.
All right. So to I mean, we can use G, but in terms of whether or not the temperature will increase, it's based on the effect on the internal energy. So these equations, so I have to make sure that the signs are correct. So let's see if we use the signs correctly. So if work is being done on the gas, that has a positive effect on internal energy. If if work is being done by the gas,
As a negative. Right.
like, yeah. All right. So if there's an increase in internal energy, there's going to be an increase in temperature. So I would use the first law of thermodynamics rather than trying to explain it
Charles
in
law.
general. So
Okay, sir.
back to 2021. If I can open it, it's so long to open. All right. One of the things that I'm going to do is I'm going to put in the folders, they try to put all the derivations one place. So instead of trying to do the derivations today, so pick out the derivations from module one. So like the projectile stuff, projectile motion, um, that's the things about data. So look through. I had a document with the derivations. I'll have to search for it. If not, I'll just redo it. This is 2021. This first one looks like a graph.
Velocity time graph, acceleration.
Alright, let's see. So best way we can do this one now.
I feel like I've done a question similar to this before.
You see, I have done something similar to this.
I believe so, sir, yes.
Alright, so we don't necessarily need the graph to talk about what's happening at the different phases. Just look at the table and then we can describe. So describe the motion of the parachutist from the time she jumps out of the airplane to the time she hits the ground, clearly explaining what's happening at each stage. Alright, so looking at the time and the velocity from 0 to 20, what's happening between 0 and 20?
She's accelerating.
So she's accelerating. So from rest, you see acceleration from rest.
To 50 meters per second.
Alright, so that would be like the max, the terminal velocity.
Yes, she reaches terminal velocity at 50 and then plateaus.
So that would be 20 to time 20 to
40.
40.
She's at terminal velocity. So she's at constant velocity. And then from 40 to 40, she's decelerating.
So where is it? Let me scroll down a little bit.
I can only assume that she's pulled the chute at this point.
Yeah, so if she's decelerating, we reach now 40.
5 to 60. She's at constant motion after pulling the parachute. Right, the terminal velocity of pulling the parachute, I would say. Is that how you would describe it?
So we can say that the velocity decreases 40 to 45. So that's because of the opening of the parachute.
Yes.
Alright, so we'd have a decrease in the velocity, and then from 45 to 60, what you say happen now?
I would say terminal velocity with the parachute. With the parachute open, as in it's been pulled. Because we're at constant velocity again. And I don't think I have another way of explaining it.
Yeah, so it's back to
terminal velocity.
Uh-huh.
And then at 60 to 62, she's hit the ground, just stops back at rest.
Alright. Yeah, so that's it. So so I didn't have to do the graph to see that. Um, identify the two major forces acting on the parachutist during the time intervals 20 to 40 and 45 to 60.
Wouldn't that just be weight and drag?
Yeah, yes, it would.
So weight and drag forces. So back to circular motion.
Ah, this again. So the car is accelerating, although its speed is constant because it is constantly changing direction, which is changing its velocity, which dictates its acceleration. That's probably not a 4 mark answer, though.
Alright, so because it's so much marks, you probably want to define what acceleration is. It's all of 4 marks. So
Okay, so acceleration is the
The
rate of
interchange of
change
velocity.
of velocity,
with time.
and velocity is a vector quantity. So the vehicle changing direction is causing a change in velocity, which will cause a change in acceleration. That sounds more like a 4 mark answer, I would say.
Yeah. Right. So yeah, yeah, for earn the 4 marks. Alright, let's see. So it's changing velocity. The velocity is changing, so it is accelerating. Alright. So I guess the next question is going to be calculation. So for the car and the driver, calculate centripetal acceleration. So here's the scenario for the car and the driver. Calculate centripetal acceleration. All right, what's the equation for centripetal?
That's v squared over r.
Yeah.
So we can write it in terms of omega or velocity, but we have velocity. So
And our velocity is 80 over our r, which is mils. Mils is our.
that's the acceleration.
No, no, that was the r. So the acceleration is 64.
Wait, the 200 in the question was the diameter or the radius?
Diameter, which is why I divide by 2.
Oh, okay. So yeah, it's 64.
So acceleration 64 meters per second.
Squared. Yes, sir.
All right. Fine. Calculate the normal reaction force. The normal
Don't I just have to calculate the weight?
weight.
So that is this times 9.1 So is it 6,670.8?
That's the weight.
Yeah.
So weight mg. You said that's how much?
Yeah.
6,000.
670.8.
Wait, what was the
Because
angle
it
in the question?
So what was the
angle.
angle?
Did they give us the angle?
I did not working out
Oh,
thinking of
50.
that.
Yeah. So remember that. That's why I did. I make sure to talk about resolving vectors. If you look at the normal reaction force, you realize that it is a component, the weight.
So it is sine
So reaction, there's a reaction force going up, which is equal to the weight. That's the reaction force. Well, the vertical component of the reaction force, which is equal to the weight. Normal or reaction force.
by sine 50 it was. Yeah, no, this was not 50.
Yeah, 50.
Oh, it is it. Okay. So I have 878.1 newtons. My bad. 8,708.1.
How much is it for the normal?
For the normal, I said I got 870, no, sorry, 8,708.11.
8,708.
8.11. Because you would divide the weight by sine 50.
Oh, wait. No, the angle. Sorry, that 50 is the banking angle. Sorry. That that 50 should not be here. It's not this.
Should be underneath the car. Wait.
No, that 50 is not here.
It,
Yeah, that 50 is actually here. So this is something you have to remember about when it comes down to banking angle. It's here. vertical component of the weight would be adjacent to the angle. Alright.
Wait, sir, repeat that.
So banking angle, how it so where you see the is the dotted line that represents the banking angle. Right? It's not it's the same as the angle up top there. So it's not that 50 is not here. That's a common misconception. So the 50 is not here. No, this is
Not 40.
Yeah, it would be 40.
yeah, that would be 40. But then, so if you're using sine, you'd have to use 40. If you're using the 50, you
So,
have to be cos. So
so so the answer changes to 10,377.92.
10,000 or 300.
700. Oh, sorry, 800. No, no, it's three. I'm looking at the calculator, but it's around 377.92.
So 598.
Chance.
All right, centripetal. Find the term. All right, let's. Even though they didn't ask, let's just go ahead and ask. Did they? No, they actually gave us authority. All right, I think that's decent. That's decent. All right, the next part. Define the term geostationary satellite. So I think that was the next question. Yeah, normal reaction force.
Yes. Was that a satellite that had the same angular velocity of the Earth? Or, yeah, it's something like that. A satellite that had the same angular velocity to that of the Earth, I think.
Alright, so same angular velocity. Alright, for the 2 marks, you'd have to mention the period for sure, since it's 2 marks. Um, so it would have to be equal to the period of Earth, if you want to say 24 hours. So it orbits the Earth with a period equal to that of Earth. So that's why it seems stationary. Right? You can talk about it appearing to remain at the same place, or you can talk about it's located over the equator. So that's how it keeps that same period as Earth. So that's the geostationary satellite.
Wait, sir, repeat the definition.
So, sir, for 2 marks, you could say a geostationary satellite is a satellite which has the same angular velocity of the Earth, giving it the same period of the Earth.
So it orbits the Earth with the same period, and it appears stationary. Right? So it appears stationary. All right, the next question says to state the physical characteristics of the Earth which determine the fixed orbital radius for a geostationary satellite.
Would it be the mass of the Earth? Would that be one of them?
Sorry. Yeah, so mass, Earth's mass.
In the chat, Aaron said the mass and the gravitational force.
Yeah, so gravitational strength. Yeah, so the Earth's mass, gravitational strength. And then the next question says state two applications of geostationary satellites.
I know one of them is it's used for like weather forecasting, and it's also used for like telecommunications.
Right, so weather monitoring, um, telecommunications, yeah. Let's see how much. So it's harmonic motion with a spring. We did the conditions. Do we want to do the Alright, so we can probably, is this similar to the question we did earlier with this, a wooden block is connected to a light spring shown in figure 3, simple harmonic motion.
Oh, it's similar indeed to the one about that is spring constant as 30 and something else is like 3, I think.
But this one is with the spring, so it might be different in terms of the calculation. So you are given the 20 oscillations in 8 seconds. So we can use that information. We're given the spring constant. Alright, so let me go to the first question. So for the system in figure 3, calculate the mass of the wooden block. So look at the information that we have here for a spring. What equation do we have for a spring?
Sir, the equation I would use is omega squared is equal to k over m.
omega squared is equal to Q. K over M. Or, I mean, you have the time. All right, let's look. What is, we know that omega is 2 pi over T. So, I mean, you could have just used the equation for time period if you knew it, which would have been,
Oh yeah, t equal 2 pi root m over k.
so that's for a spring. So they want the mass, you're trying to find the mass of the wooden block. So we'd have to, how would we make mass the subject at this now?
You would have t equal 2 pi times root m over root k, and then you would just cross multiply and then get m.
Root m over root k. Why that sounds so complicated now.
You know the square both sides.
Yeah. So could I move the 2 pi? You could have t over 2 pi.
Then square both sides.
Square root to get rid of the square root of m over k.
And then throw k over. Multiply.
So it'll have t squared times k 4 pi squared. Alright, anyway, you feel comfortable, but yeah. Anyhow.
Wait, what was k? Wait, what was k? Was it 26?
Yeah, 26 and a half.
So let's see.
I got the mass to be 0.11 kilogram.
So 0.11.
Yes, sir.
Alright.
I got the mass to be
It was 4 marks. You got something
0.
different?
Yeah, I think I may have done something differently. I got 0.010.
It's probably just based on rounding and that type of thing.
Yeah.
All right. Angular frequency of, so angular frequency here is what symbol we're talking about now.
I can only assume that it's not the same W.
Isn't this just asking for omega, or is it not? I don't know.
Yeah, it's still omega, so it might sound weird,
Oh,
but still.
So I'm realizing that anything with angular is almost always going to be omega.
so it's just 2 pi over t.
Yeah, so it's 2 pi over t.
I got it to be 5 pi.
5 pi, so about 15 point something.
That's
Wait, what?
50.71.
Wait, what? I may have done something
What is,
incorrectly.
cause what is t? Don't you know t?
What did you use as t?
Was T not 8? Was it not 8 seconds?
Yeah, but the 8 was for 20 oscillations, though.
Oh, it's 8. My bad. Yes, it's 5 pi.
Alright, so t would be 0.4 time period. Alright. Maximum velocity. Calculate the maximum velocity of the wooden block. Maximum velocity of the wooden block.
What was our uh amplitude?
Did they give us amplitude?
It would make life easier. They did.
Oh, 2 cents.
Have to
So
change
we'd have to
meters.
convert it.
So 0.02. So I believe that it is 0.314.
0.314. So this, that's coming from the equation V max.
Vmax equals amplitude times angular. Actually, this might be wrong. Is the angular frequency?
I got 0.314.
Okay.
Because velocity is omega times amplitude. So, yeah.
Yeah.
So 5 pi
Okay.
times 0.02.
Alright. Alright, so all you would have to do in this sketch is just make sure you use the values, so you could input the period values for the period time period, and ensure that you're showing one complete oscillation each time um, for the correct time period is how much marks? This
5?
It's 5 marks.
Alright, and it should have a max, so it would look like the damping diagram. So the max amplitude should be 2.0, and the amplitude should be getting less and less.
Yeah. And then you just repeat that 5 times.
Yeah. Alright, identify that's showing up in the question. Identify the phenomenon depicted by the waveform sketched in and state two real life situations in.
Sir,
So I kind of said it already. So damping.
sir,
Uh-huh.
for the one where you sketch it, is it that as like you go up, so like we're going for half the wavelength, the first half, like so we're going up like from 0 to 1, and then past 0 and go back down to -1. Would the first one be 2, and like as you go down on the negative side, would it be like 0.8, or would the whole wavelength be 2 and then it would be 0.8,
Or if so,
like 1.8?
yeah. So keep each wavelength. So each wave cycle, I should say, let it have the same amplitude. So if it starts at 2, if you're starting at 2, you should have a positive 2 and a negative 2, and then you decrease in the next cycle. Keep. So if the next one is 1.8 and then 1.8, and then you move to 1.5, 1.5. So it should be a gradual decrease. So it's not decreasing within the cycle, it's decreasing after each cycle, if you get what I say.
So it'll be 5 cycles in.
So 5 cycles, 5 different amplitudes.
Okay.
Alright. So this is damping. What are some real life situations where damping is applicable or is used?
Car shocks.
Yes, car suspensions, the suspensions in doors, so like doors that can be damped, um, with uh, those those things. Any other example you can think about where damping? So you can look up some more examples of that. All right. All right, let's try and finish this one. So this is the last question because we have to run. But in terms of threshold of hearing, we've heard that concept before. What is the define the term threshold of hearing and states its value for a healthy young adult?
I do not know the value off the top of my head for a healthy young adult, but I remember that the threshold of hearing was something like the minimum amount of audio that an individual can hear, or something like that.
So the minimum. All right. So it essentially is the intensity at which sound is just audible. All right. So it's the intensity. It's referencing the intensity of the sound. All right. For a human, so you can make a note of that. It's going to be 1 times 10 to the minus 12.
That's per meter squared.
What's that?
I think 1 times 10 to the negative 12 watts per meter squared.
Yes.
Is it watts per meter?
Yes. And then in terms of the equation for the relationship between the sound level in decibels, what is that equation?
Log I log over I think that no, I don't think that's the one for this one.
So
Wait, sir, what did you say the threshold of hearing was again?
1 times 10 to the minus 12, Wm to the minus 2. So you have I over I naught.
So can you repeat what that is?
What are we answering?
Yes.
Oh, sorry, right. Because I didn't show you the question. Write an equation to show the relationship between sound intensity in dB and threshold of hearing, IO. So that's what we're answering.
Okay.
So the 10 log 10 all log I over I naught.
Stuff like
So 10 log, yeah.
So what my question for the logs, is it like do you need the 10 to be there?
If you need one,
Does it have to say 10
10.
logs?
uh, yeah. I mean,
No,
there's,
I'm
there's
not.
probably there's probably another way to put it. You know of another way to put it?
No, because logs is one of my weaker points. I'm not really sure how it goes, but I'm pretty sure there's something like what is it 10 10 log base 10 or something equal one or something like that. I don't
Oh,
remember the rule,
oh
but it's
no,
like
no, no, no.
Wait, sir, what was the equation again? It was 10 log. What was in the bracket?
I
I over
over
I
I
naught.
naught.
I what?
So
I
just
the
I.
the symbol is there.
All right. So that's the sound level. That's sound level is equal to that. Sound level in decibels. Plus. Okay.
So this is the equation that relates decibels to the threshold of hearing.
Yeah, the sound level and the threshold of hearing. Alright, so you can use that at a party. The average sound intensity level is found to be 90 decibels, determine the intensity in that.
So it be is 90 divided by wait, no, wait, hold on. 90 is equal to 10 log I over I naught. So wait, hold on. I think I know.
So with transposition, um, the sound intensity is 900 equals log I. So it would be
900.
yeah, no, this
Or the
oh no, it's
90 is
dividing.
what,
My
God?
bad. Nine
So 9.
equals log I over I sub 0. And then we use the what log means. So it's going to be 10 to the ninth power
So the
equals
inverse, I would say anti-log. So can do the anti-log to get rid of the log on
yeah,
both sides.
log inverse. And now we have I over I naught. Is that not it? Or did we get what I or I naught?
Remember they asked you what I naught was. What does I naught represent? What does I naught mean?
Threshold of hearing.
The threshold of hearing.
Oh, so I is equal to 1 times 10 to the negative 3.
1 times 10 to the negative 3.
1 times. Yeah.
So 1 times 10 to the negative 3.
Wait, sir, could you go back on the working out real quick? So wait, how did you go from 9 to 10 raised to the 9?
Because remember, log is base 10. Log base 10. So
Yeah.
if you look on the calculator, the well, depending on the calculator you're using, the inverse of log is to raise it to is anti-log, let's say. So anti-log would just be 10 to the power of. So I don't know, are you using a calculator, or is just it's usually the anti-log is usually on top of it's on the same button, say that if you use second function or shift or to get the anti-log.
So I got 10 times, I got 1 times 10 to the negative 3.
Oh, shit. I get it.
Okay. Alright. Then the final question. A student has been at a party for 3 hours. Determine the amount of energy incident on his area.
Wait, sir, what was the answer for the previous question? What was the
Intensity.
answer? Yes, sir. What was it?
-3, because we know the threshold is 1 times 10 to the -3 I naught. So 1 times 10 to the 9 times the threshold. And times 10 to the -3.
The student has been at a party for 3 hours. Determine the energy incidence of his eardrum if its surface area is 0.5. What? So what formula would you use for this? Would it be the same? No, that's not sound intensity. It said the energy.
Yeah, energy. Alright. Alright, if you look at the unit of the threshold, kind of gives you, so we know that the unit for the threshold is that to the -2. So it kind of gives you a clue as to what the intensity is. So basically power over area. If you look at the unit, watts and per meter squared. And power, what's power?
Energy over time.
Energy over time. Here. So what do they want? They want determine the amount of energy incident on. Yeah, so I think we have enough to calculate this. That's all. Calculate energy. Because
What's energy over time, right?
yeah. So we know I, it's the same I from the previous question, 1 times 10 to the -3. We know the time, we know the area. So it's just a matter of rearranging and substituting. Alright, so the time, convert to seconds, 3,600.
So it's 1 times 10 to the -3. What was the area they gave us?
The area.
It was 0.5 squared.
0.5?
Wait, no, it was 0.5, I believe.
Was it in meters or centimeters?
It was centimeters.
Centimeters. Boy. Centimeters squared to meters squared. That is.
Wait, sir, real quick. How did we get that equation again? How did we get that equation again?
How did you get the equation?
Yeah, for the power thing. E over TA.
So the intensity is the power over area. So intensity of sound is really power over the area. So that's the
And then
so
and then for the energy over time. You just converted the power into energy over time.
Yeah.
Okay.
So would you divide by 10,000 to get it in meters
Meters,
squared?
yeah. Meter cube square. With a cube.
Yeah, meter squared, yeah.
Meter square.
So it is 0.5 divided by 10,000 instead of the 100. So that's 5 times 10 negative 5. I know I should just have watts if I'm looking at it dimensionally. So it's 5 times 10 to the minus 8. And then the time was 3 hours.
Hours.
So it is, and it's converted to seconds. So it's going to be 3 times 60 times 60. And I get 10,800. So it's going to be 5 times 10 to negative 8 over 10,800 is equal to 4.63 times 10 to the negative 12.
Wait, what was the intensity again?
1 times 10 to the minus 3.
To the minus
Yeah.
what? It was what? To the minus
3.
what? To the minus 3.
Yes.
Okay, so then that means that I got 5.4 times 10 to the negative 4.
And that sounds more like it. So let's see what it is. 5.4 times 10 to the negative 4.
Is that the answer?
Yeah, that is the answer.
Oh, okay.
All right. All right. So as I said, I will populate that folder with the derivations and anything else I can find, so you can check back probably um, tomorrow or Wednesday in terms of the physics folder. All right. So use the document. Don't just study the calculations. Don't just practice the calculation. There are some other theoretical stuff. So whether it's global warming, just go through the syllabus and look at some of the experiments and the theoretical things. So don't just study for calculations, please. All right. So we have to stop it here.
Sir, could you send the link for the folder again, please?
Uh, where is it? Where is it? Where is it? Where is it? You see it?
Yes, sir.
Yes, sir.
All right. All right, gentlemen. So, all the best and make sure you practice your elements here. I will see you for those who have chemistry. I'll see you tomorrow for chemistry.
Yes, sir.
All right.